So welcome everybody to the seminar. So we are very happy to have Professor Hu Yong as our speaker today. And Professor Hu Yong from Shanghai Jiao Tong University. And so he was student of Professor Men Chen and been working in KIAS for a couple of years and now working in Shanghai Jiao Tong University. So, so he's going to talk about the modular spaces of three-fourths on the Noether lines. Okay, thank you, please. And when the canonical volume is larger than 0, V is said to be of general type.
we have the following example. We can consider the smooth hypersurface of degree D in Pn plus 1. By the adjunction formula, we know that the canonical divisor is just over D, D minus N minus 2. So when D is larger than N plus 2, VD is of general type. So there are a lot of varieties of general type. Our main goal is to classify varieties of general type. And you will find that when the dimension is larger than or equal to 2, if you just blow up some point, you will get another variety, which is also of general type, and they are birationally equivalent. So how to classify them? The first step, we have to find some good model. Okay, now let V be a varieties of general type, smooth varieties of general type. And by the work of BCHM, you can contract some negative curve. You can get something called minimal model. Minimal model means that this is MMP, minimal model program. XM has at worst Q factorial terminal singularities. And the canonical divisor is NF. And because we only consider the varieties of general type, so this is not only NF, but also big. And you will find that the canonical volume of V is just the canonical volume of this minimal model. And this is the self-intersection number of canonical divisor. If the dimension is larger than or equal to 3, the minimal model is not unique because of the existence of flops. But you can contract something, get the so-called canonical model. Canonical model means that this variety has at worst canonical singularities, and the canonical divisor is ample. So the canonical model is unique up to the isomorphism. So if you want to classify varieties of general type, you only need to classify the canonical models or minimal models. Because the canonical volume and the geometric genus are birational invariants, So you can consider the following set: mkn pg. Pg is a non-negative integer, and kn is a positive rational number. This is the coarse modular space. Parametrizing. Canonical n-folds with canonical volume Kn and geometric genus PG. Sorry. Oh, so what happened? By the work of Mumford, Fiwek, Kolar, and Shafet-Baron, or Alexeev, and many other people, we know that this is not only a set, but this is a quasi-projective scheme. So we can study the geometry of this modular space. You can ask the following two basic questions about this modular space. The first question is, when is this modular space non-empty? This is related to the geography of varieties of general type. The second question is, if this modular space is not empty, then we can study the geometry of this modular space. For example, you can study the dimension and the number of irreducible components and also you can study the number of connected components. Okay, let's first look at the case when n is 1, which means that x is just a smooth curve. When n is 1, we know that the first question, mk1 and pg, this is non-empty. If and only if k1 is just 2pg minus 2. This just follows from Riemann-Roch formula. This k1 is just the degree of the canonical divisor, and pg is larger than or equal to 2. Because we are studying the varieties of general type. And the second question, we know that M K1 PG. You assume that this is K1 is just 2PG minus 2. So this is not only a scheme, this is a quasi-projective variety. Of dimension 3 PG minus 3. So for curves, both two questions are answered. So now we can consider the case when n is 2. Irreducible. Variety means that it is irreducible. So when n is 2, this is a surface. So now let X be a canonical surface. In dimension 2, we know that canonical singularities are just the singularities called ADE singularities. So both of them are hypersurface singularities. So the canonical divisor is Cartier. And we know that the canonical volume, in this case, this is just a positive integer. For the first question, we have the following famous inequality called Noether inequality. It states that the canonical volume Kx square is larger than or equal to 2pgx minus 4. And this inequality is optimal, which means that for any integer pg larger than or equal to 3, there exists a canonical surface X such that geometric genus is PG, is this number, and the canonical volume is 2PG minus 4. So this is optimal for any PG larger than or equal to 3. So in this case, when n is 2, and for PG larger than or equal to 3, and K2 is 2PG minus 4, we know that this is the modular space is not empty. How about the geometry of this modular space? It was studied by Horikawa. Horikawa proved that now we fix PG is larger than or equal to 3. This is a positive integer, and K2 is just 2PG minus 4. We know that the modular space MK2PG is not empty, and Horikawa proved that this modular space is irreducible if this canonical volume is not divided by 8. And when the volume is divided by 8, it has 2 disjoint irreducible components. And the dimension of this modular space are also computed by him. So let me draw a picture. This is the geometric genus, and this is the canonical volume of surface. This is 1, 2, 3. This is the knot line. So for the case when PG is larger than or equal to 3, and the surface on this line, the geometry of this modular space is clear. So how about the case when the geometric genus is 2? We know that the lower bound is at least 1 because the canonical volume is an integer. And when the geometric genus is 1, the lower bound is also 1. So you will get the following picture. The invariance is here. And the case when PG is 2 and the volume is 1, it is also studied by Horikawa. So PG is 2 and the canonical volume is 1. We know that the canonical surface is in fact a hypersurface of degree 10 in this weighted projective space, P1125 of degree 10. By the adjunction, you will know that the canonical divisor is just the OX1. So the geometric genus is 2 and the volume, canonical volume is 1. In fact, all canonical surface is a hypersurface of degree 10 in this weighted projective space. So the modular space is irreducible and of dimension 28. And if the geometric genus is 1, we know that the lower bound is also 1. In this case, it is proved by Catanese that the canonical surface is in fact a complete intersection of 2 hypersurfaces of degree 6 in this weighted projective space, P1, 2, 2, 3, 3. So the modular space is also irreducible and of dimension 18. And when the geometric genus is 0, the lower bound is also 1. This surface studied by Reed, Miyaka, Catanese, and many other mathematicians. So, but the modular space is still not very clear. Okay, this is the story for surface. Now we are going to varieties of higher dimension. So how about the case when n is larger than or equal to 3? For high dimensional case, there are several difficulties. The first difficulty is that the canonical volume is no longer an integer. It's not an integer. And it could be very small, even for threefold. You can consider the following examples constructed by Fletcher. This is the degree 26 in the P45. Oh, sorry. FLET. Oh. 20. Oh, is this number correct? Yeah. You will find that the canonical volume is 1 over 420. So it is very small. You can still ask the question whether the inequality of Noether type holds for threefolds of general type. So now, from now on, I study the case when n is 3. Okay. In fact, the Noether inequality exists for threefolds of general type. First, it was proved by Yongkai Chen and and Meng Chen and Chen Jiang. So this is Yongkai Chen and Meng Chen. They proved that if the geometric genus is if either so X from now on, X is also canonical threefold. If the geometric genus, either the geometric genus is less than or equal to 4 or larger than or equal to 11, then we have the optimal inequality, Noether inequality, which states that the canonical volume is larger than or equal to 4 over 3 Pg x minus 10 over 3. The optimal is means that you can find infinitely many PG such that this equality holds. So the remaining case is that geometric genus larger than or equal to 5 and less than or equal to 10. This was proved by Meng Chen and myself and Chen Jiang. Okay. This is Meng Chen and myself and Chen Jiang. So if PG is larger than or equal to 5 and less than or equal to 10, then we have the canonical volume is kx cubed is larger than or equal to 4/3 PGX minus 10/3. So for any threefold of general type, this inequality holds. And we also prove that without these assumptions. So for any threefold satisfying of general type, any canonical threefold, satisfying this equality, then the canonical image this is the image of the canonical map. Because X is of general type, so this is positive, which means that the geometric genus is at least 3. So you can study the non-trivial canonical map. And when the equality holds, and then the canonical image is a surface. Okay, here we have to assume that for any canonical threefolds, and the PG is larger than or equal to 5, and PG congruent to 1 modulo 3. So this equality does not hold for every PG. But combine this the work of Chen Jiang and I work with Meng Chen and Jiang Chen and our previous work with Hong Zhang. We know that the optimal inequality should we know the following. Let X be a canonical threefold. Then we have the refined, we call it a refined Noether inequality. The canonical volume is larger than or equal to PG minus 3 plus 1/2. This round up of 2PG minus 2/3. It takes the round up. If you remove the round up, this is just this inequality. And in fact, this inequality is optimal for every PG is larger than or equal to 3. So the next question is how to study the modular space of this threefold. Okay, now let PG is larger than or equal to 3, larger than or equal to 5, and K cubed is PG minus 3 plus this one. We study the you can larger than or equal to 3. We would like to study the modular space of this M K cube PG. And when this equality holds, we say that X is on the not line. Our first theorem, this is we study the modular space for threefolds on this not line, and we assume that PG is larger than or equal to 5, and K cube is this number. We prove that the first theorem for all PG is larger than or equal to 13, and N is an integer. It can be 0, 1, or 2, depends on the geometric genus, such that PG is congruent to N minus 2 modulo 3. Then M, the modular space, is a union of alpha PG. This is a number, depends on the PG, unirational strata. And alpha PG is the following number. If N is 0, then alpha PG is PG plus 6 over 4, and take the round down. And if N is 1 or 2, then it is this number, PG plus 10 minus 2N. And the second statement, we study the number of irreducible components. Number new PG of irreducible components of this modular space is at the most alpha PG and at least alpha PG minus beta PG, where beta PG is a number like this. When n is 0, this is PG plus 8 over 78 and take the round down. When n is 1 and PG is larger than or equal to 20, it is PG plus 61 over 78 and round down. And when n is 2 and PG is larger than or equal to 45, it is PG plus 36 over 78. And for other case, this is 0. So when PG is small, the number of irreducible component is just alpha PG. And you will find that the number of irreducible components grows linearly with respect to PG. Okay, this is, we assume that this PG is slightly larger than or equal to 13. And when PG is small, the third statement, we study the dimension. This is computed. PG plus 2 plus 2n over 12 and plus. In fact, the modular space is not equidimensional. This is the dimension of the one with the irreducible component, which is the dimension is maximal. This is the maximal one. Okay. This is also our joint work. C, H, P, and Z. If PG is larger than or equal to 5 and less than or equal to 12, we also consider the K cube is this one, this number. Then M, the modular space, consists of also new PG, unirational irreducible components. And the number is like this. When PG is 5, 6, or 7, the number of irreducible components is 2. And when PG is 8, 9, 10, the number of irreducible components is 3. And when PG is 11 or 12, the number of irreducible components is 4. So this number is small. This is the irreducible component of this modular space. In this case, some strata will contained in other strata's chloride. The irreducible components is closed in the modular space, but this is not closed. And the dimension is also computed. The dimension of each component are computed, but it is a little long. So this is for the case when PG is larger than or equal to 5. You may ask, how about the case when PG is less than or equal to 4? And when PG is 3 or 4, it is studied by the modular space. Irreducible. These are studied by my previous work with Meng Chen and Chen Jiang. So when the geometric genus is larger than or equal to 5, you will find that the modular space is not irreducible. How to prove it? We need the following definition introduced by Coughlin and Pinatelli. It is called simple fibrations in 1-2 surface. This is a fibration such that X is just a threefold with at worst canonical singularities. And B is a smooth curve. Pi is a fibration. So all the fibers are connected. And if Kx is pi ample, and for any closed point P in B, you can consider the canonical ring of the fiber XP. The canonical ring is generated by 4 elements. With respective degree 1, 1, 2, 5, and related by a homogeneous equation of degree 10. So the fiber is just a hypersurface in P1125 of degree 10. Then the fibration pi x over b to b. This is called a simple fibration. In 1-2 surface. What's the meaning of 1-2 surface? 1-2 surface means that the canonical volume of this surface is 1 and the geometric genus is 2. And if this surface is canonical, I said it before, it is a hypersurface of degree 10 in P1125. So the simple fibration means that every fiber is a hypersurface of degree 10 in the weighted projective space P1125. And there is the following conjecture. There exists epsilon larger than 0, such that for any threefold, canonical threefold, X with the canonical volume is less than or equal to 4/3 PG X minus 10/3 plus this number epsilon. And PG sufficiently large. So for any threefolds which is close to this equality, then X birationally admits a simple fibration in 1-2 surface. So for any threefolds, the conjecture that for any threefolds close to this equality, birationally you can find some other birational model of X which admits a simple fibration in 1-2 surface. And we prove that this conjecture holds when this number is very small. Oh. Our first step, we prove that every canonical threefold X on the knot line which means that the canonical volume is PG minus 3 plus this number. Birational with PG X larger than or equal to 5. Birationally admits a simple vibration in one-to surface. Over P, this is a simple vibrations of one-to surface over P1. Here, the number 5, the bound 5 is optimal because when PG is 4, you can consider the double cover of P3 branched along a surface of degrees 10. It does not admit birational, does not birationally admit simple vibrations into one surface. In fact, we prove that the conjecture holds for epsilon is 1/2 when PG is larger than or equal to 11, and for epsilon is 1/30 when PG is larger than or equal to 5. So we find a birational model such that on that model, there is a simple vibration into one surface. Okay, then our second step, we study these vibrations. So now we assume that we have a simple vibration onto P1. This is a simple vibration. Into one surface. So we know that every fiber can be embedded into P1125. So now, globally, it is embedded in the following P112 bundle. P1125 bundle over P1. So X is a hypersurface in this P1125 bundle. And in fact, this one is a toric fourfold Fx. and we have n is this number. This x here, kx is still naive. And you will find pgx is 3d minus 2 plus n. So you can get d from the geometric genus Pg. This is a number determined by Pg and n. And you can consider the following Hodge bundle. Because the fiber is the geometric genus of the general fiber is 2. So this is a rank 2, is a vector bundle of rank 2. And it is the vector bundle over P1, so it splits. You can write it as this one. D naught plus OP1 delta minus D naught. And the delta is degree F rho star omega x over P1. And D naught is the number less than or equal to delta over 2. So for this, N, D, and D naught, Fx is in fact isomorphic to the following toric fourfold. It acts on this C6 like this one. T naught, T1. This is a coordinate. X naught, X1, Y, Z. So this torus acts on this vector space with weight matrix like this one. And X is a hypersurface in this toric fourfold. X is of pi degree minus 4n and 10. So you can write down the equation of X like this one. Z5 equals to something Y5. And here there is a coefficient plus something like this one. In our last step, we study the modular family. MDN D naught of hypersurface. X dn D naught in this toric fourfold. We call it F D n capital N D naught. With n less than or equal to 2. It is easy to check that n is less than or equal to 2 because it satisfies the equality. So we have MDN, it maps to the modular space with image is this one. And this one is in fact quasi-finite. Because for fixed canonical threefold, it has at most finitely many minimal models. So this is a quasi-finite morphism. So the dimension of these two are the same. This is the image. And combined with, together with Pinatelli's deformation technique, we know that when so VDN D naught is in the closure of this strata. When n is 0 and D naught larger than or equal to D, or n is larger than 0 and D naught is larger than or equal to D plus. And for most D naught less than D, less than or equal to D, the closure of VDN D naught forms an irreducible component of this modular space. Then we finish the proof. Okay, I think I stop here.
Thank you very much. So, any questions? So,
VND is just the image of this this modular family.
So how do you count the number of irreducible components on this kind of framework?
So when D naught is now first the modular space has this strata, and when D naught is large, then it is contained in the closure of this component. And when D naught is small, we prove that it is the closure is in fact an irreducible component. You can study the canonical map of this threefold, and the map is either a Hertzsprung surface or a cone over a curve of minimal degree. So you will get a family of Hertzsprung surface.
Yes.
And if you so there is a restriction of this the index of this Hertzsprung surface Fe.
Mm-hmm. Yeah.
Yeah. And we also compute the dimension of this of every strata. So okay. when D naught is small, we prove that itself, the closure of this one is in fact reducible by considering the dimension of this strata and the deformation of the canonical image.
And how about kinetic components? Is it possible?
We don't know.
And any other questions?
So, is there any similar kind of vibration structure theorem or conjecture for surfaces on the Noether line?
For surface,
Yeah.
I think for surface, we know that when the canonical volume is 2pg minus 3 and the pg is large, then or less than or equal to 2pg minus 3 and the pg is large, I think it admits simple vibration. Oh, sorry. I don't know. Maybe for surface on the Noether line, we know that it admits simple vibrations. But for when the volume is larger than 2pg minus 4, I don't know.
So somehow geometrically, there's like some kind of recursion thing. So you have like genus 2 curves and then the 1-2 surfaces and then the 3 folds of this form. And so is there also a recursive relation between the formulas for the Noether line, like that reflects this kind of geometry, or not really? Like, for example, your formula for the 3 folds, it contains the degree of the canonical of the curve, but I mean, like 2g minus 2.
In our case, if you consider the canonical linear system of our threefold, it is a surface. In our proof, we prove that this surface is in fact a Horikawa surface. So it admits a simple vibration into 1-2 surface or into curves of genus 2. So it is they are related.
Okay.
Where does the unirationality come from in the proof?
Because this X is a polynomial in this invariance. So the deformation is just the change the coefficient of this family of this polynomial. So it is unirational.
And a stupid question is the union of unirational strata. Is it of Kodaira dimension?
Kodaira dimension is negative infinity.
Is negative infinity.
Yeah.
Okay. And do you know the Kodaira dimension of the smaller n cases, like smaller dimensional cases?
Small dimension of what?
Of the moduli spaces.
So
you're looking at n equals to 3, and then you have Kodaira dimension.
Yeah.
Yeah. So for n smaller than 3, do you know the Kodaira dimensions of the moduli spaces when they are non-empty?
Usually it will be very complicated. And if you consider surface on the Noether line, then the modular space is also unirational.
Oh, okay. Yeah, thank you.
So do you have any expectation for higher dimension?
I don't know. I don't know how to do for high dimension, even for 4-dimensional case. And when the canonical map is generically finite, it is easy to get the inequality. So if the canonical map is generically finite, then the canonical volume, it is very easy to prove that. But if the canonical map induces a vibration and with general fiber of curves, we don't know the slope. You mean this inequality? Yeah, this is optimal if you assume that the canonical map is generically finite. And the equality case, I think, was studied by Professor Yongkai Chen before. Yeah. One half, yeah. Yes. Mm. That's a. Mm. Mm. 对，对，这是。嗯。就是我们后面这一步的话，就是说这个 toric fourfold 对吧？就是它是 toric fourfold 这一步，我们需要这个 n 是要，就是只要这个 n，就是我们有一个大 n 这个数对吧？大 n 那个数的话，它是小于等于4的时候，这是一个 toric fourfold，就是这个 P1125 phi bundle 是真正是一个 toric fourfold。但是当那个大 n 等于5的时候，也就是说它离这个我们的大 n 是这么，你可以这么看。大 n 其实是衡量了它与这个我们4/4p，就是说你这个 volume 如果等于4/4pgx 减去一个10/10，然后我们加上一个6分之大 n。当这个大 n 小于等于4的时候，我们证明这个 P1125 phi bundle 一定是一个 toric fourfold。但是当大 n 等于5的时候，这个东西我们有例子，就是说它不是一个 toric fourfold，所以你就没有办法把这个 equation 这些东西给写出来。就是其实就是说你可能就是说对于大 n 小于等于4的时候，也就是说你在那个 我们 note line 的话，就是 n 是小于等于2，这个是在 note line。你往上一点可能还能做一点，就是说 n 等于3啊4的时候这时候应该还能做。但是当你 n 大于等于5的时候，因为这个虽然说它是 simple vibration，但是这个东西不是 toric， 它不是 toric 的话，你去研究它的 modular 就是说你不能把它就是用写方程这种形式，所以就会很复杂。虽然说我们在 P1 上，它每一个 vector bundle 它都是以 line bundle 的之和，但是这些 algebra 之间的结构就会变得非常的复杂，因为它可能就是一些 extension， 它并不是那种之和了。我们这里就是说，我们主要证明就是 n 小于等于4的时候呢，我们有一个非常，你可以考虑这样的一个自然的一个代数，就是你从 algebra 诱导出来的，就是 symmetric to f lowest omega x over p1 到这个 f lowest omega x over p1 这个 2， 而这个是 relative 那种 bicanonical， 你把它 push forward 下来，然后这边是一个 这是一个 line bundle， 就是在我们这个情况下，它是一个 line bundle。然后我们关键的一步就是说 n 小于等于4的时候，我们可以证明这个一定是分裂的。所以它其实是这样子，这是分裂的。这个分裂的话，因为这边它是2个 line bundle 的这个，就是你做 symmetric product， 所以它和这个东西和这个 line bundle， 你就生成了这个 P112 bundle， 而且这个 P112 bundle 因为它是直和这样出来的，所以它其实是一个 toric 的 ，toric 在这里。但是当你这个 n 大于等于5的时候，这边这个可能就不是分裂的了。不是分裂的，那你的这个结构就会很复杂啊。
So in the case of n less or equal than 4, then your mu model is always 2 constant, or maybe you might have Cartier index 3. And I mean the singularities of your mu models.
For n is 3, we don't know. Even for n equals 3, we don't know whether it is Cartier or 2 Cartier. In fact, we prove that if canonical volume is larger than 4 over 3 pgx minus 3, then we have the following optimal inequality. But when the equality holds, we don't know whether x is 2 Gorenstein. It may have some point of index 3, but we don't have examples.
Okay. Any more questions? Okay, so if not, let's thank Hu Yong again. Thank you very much.
Thank you.